Alright, let's go. Number 10. The Baryon Asymmetry. Andrei Sakharov was not trying to explain why you exist. In 1967, working at the Lebedev Physical Institute in Moscow, he was trying to patch a hole in particle physics, a technical requirement for any theory that wanted to explain why the universe contains matter at all. It was bookkeeping. Housekeeping, nobody expected it to become one of the deepest open wounds in cosmology. The Standard Model predicts that the Big Bang should have produced matter and antimatter in exactly equal amounts. Every particle, a mirror image partner. When matter meets antimatter, both annihilate into pure energy. Equal amounts in, equal amounts destroyed. The prediction is clean. The math is symmetric. The universe should be empty. It isn't. For every roughly 10 billion antimatter particles produced in the early universe, 10 billion and one matter particles survived. That tiny asymmetry is the only reason atoms, stars, planets, or you exist. Something tipped the scale. Nobody knows what. Sakharov's 1967 paper, published in Soviet Physics Jet Letters, laid out 3 conditions any theory would need to satisfy to produce this imbalance: baryon number violation, C and CP violation, and a departure from thermal equilibrium. 57 years later, experiments have confirmed all 3 conditions exist in nature. The amount of CP violation measured is roughly 10 orders of magnitude too small to account for the asymmetry we observe. Physicists proposed grand unified theories with new heavy particles that decay preferentially into matter, none detected. They proposed leptogenesis, where neutrinos do the tipping, plausible, unconfirmed. They proposed that antimatter simply drifted into separate regions of the cosmos we haven't observed, ruled out by the near-total absence of annihilation radiation at galactic boundaries. Every mechanism that could explain it in isolation is either untested or insufficient. If the imbalance had been reversed, if one particle in 10 billion had tipped the other way, there would be no you reading this. No matter for it to be written on. Your entire existence is downstream of an asymmetry 0.03% wide. And no experiment has yet caught the universe in the act of creating it. What decided the tilt, and why did it decide in matter's favor? The universe doesn't just hide its beginnings. Sometimes it hides the reason anything survived at all. Alright, number 9. The vacuum energy catastrophe. Steven Weinberg was not trying to break physics. In the late 1980s, working at the University of Texas at Austin, he was trying to reconcile 2 of the most successful theories ever built: quantum field theory and general relativity, by asking a simple bookkeeping question: how much energy does empty space itself carry? Quantum field theory treats even a total vacuum as a churning sea of particles flickering in and out of existence, each contributing a tiny sliver of energy. Sum every contribution up to the Planck scale, and general relativity says that energy should curve space-time violently, either collapsing the universe in an instant or blowing it apart before atoms could form. Weinberg ran the sum. The predicted vacuum energy density came out roughly 10 to the power of 120 times larger than what astronomers actually observe driving the accelerating expansion of the universe. Not double. Not 1,000 times off. A number with 120 zeros standing between prediction and reality. Weinberg published the result in his 1989 paper, The Cosmological Constant Problem in Reviews of Modern Physics, calling the discrepancy the worst theoretical prediction in the history of physics. Later precision measurements of the actual cosmological constant, refined through Type 1a supernova surveys in the late 1990s by Saul Perlmutter, Brian Schmidt, and Adam Riess, only sharpened the mismatch. The number that should destroy the universe instead sits calm, small, and stable. Physicists propose that some unknown symmetry cancels the vacuum energy to exactly 0. But the observed value isn't 0, it's just absurdly small, which no symmetry naturally produces. They proposed anthropic selection across a multiverse of bubble universes, where we simply live in the rare one calm enough for galaxies to form. Untestable, they proposed supersymmetric cancellation. The particles supersymmetry predicts have never been found at the Large Hadron Collider. No mechanism has closed the gap. Empty space, the nothing between your atoms and the nothing between the stars, should be violent enough to unmake reality. It sits still instead, for a reason no equation has ever produced. Why is the vacuum calm when every calculation says it should be screaming? Alright, number 8. The Trans-Planckian Problem. Robert Brandenberger was not trying to undermine inflation. In 2000, working alongside Junior Martin, he was trying to trace inflationary theory's predictions for the cosmic microwave background back to their absolute origin, to check the math held up at every scale all the way down. It was meant to be a confirmation exercise. Inflationary theory, first proposed by Alan Guth in his 1981 paper Inflationary Universe, a possible solution to the horizon and flatness problems in Physical Review D, says the seeds of every galaxy began as microscopic quantum fluctuations, stretched by exponential expansion into the large-scale structure we see today. The theory assumes those fluctuations can be traced back smoothly to arbitrarily small scales. They can't. Trace the fluctuations backward far enough, and their wavelengths shrink below the Planck length, roughly 1.6 times 10 to the negative 35 meters, the scale at which our current laws of physics simply stop making predictions. Inflation's own success depends on a regime where inflation cannot be described. Brandenberger and Martin's paper, The Robustness of Inflation to Changes in Super-Planck Scale Physics, published in Modern Physics Letters A in 2001, showed that the observable predictions of inflation depend sensitively on unknown physics at scales no experiment can access, and no theory can currently model. Physicists proposed that string theory would eventually resolve the sub-Planckian regime. String theory remains unverified. They proposed modified dispersion relations that smooth the transition, mathematically permitted, observationally unconstrained. They proposed simply assuming the standard vacuum state holds all the way down. An assumption, not a derivation. Every fix borrows certainty from a domain where none currently exists. The pattern of galaxies containing your solar system was, at its origin, a calculation performed in a regime where the rules of physics are not known to apply. We built galaxies out of a blank page. If the foundation of structure formation sits in the one place physics goes silent, how much of what we call understanding is really extrapolation? The next anomaly doesn't just strain the model, it bends the sky itself. Alright, number 7. The Axis of Evil. Kate Land was not trying to find a preferred direction in the universe. In 2005, working with Ju Maguijo at Imperial College London, she was running a routine consistency check on Wilkinson microwave anisotropy probe data, verifying that the largest patterns in the cosmic microwave background pointed nowhere in particular. Standard cosmology requires the universe to have no preferred direction at all. The cosmological principle, foundational to the standard model, states the universe is isotropic, the same in every direction, on average, at the largest scales. The largest scale ripples in the CMB, the quadrupole and octupole moments, should be randomly oriented relative to each other and to our solar system's position in space. They weren't randomly oriented. The quadrupole and octupole axes lined up with each other, and both aligned suspiciously close to the plane of our own solar system's ecliptic, a direction that should have zero cosmological significance. Land and Maguijo published the finding in their 2005 paper The Axis of Evil in Monthly Notices of the Royal Astronomical Society, naming the alignment for how directly it violated the assumption of a directionless cosmos. The Planck satellite's later, higher resolution data released in 2013 confirmed the same alignment persisted. Physicists proposed foreground contamination from our own galaxy's dust and synchrotron radiation. Partially subtracted, alignment persisted. They proposed it was simple statistical chance in a universe with only one observable sky to measure, plausible, but the odds cited run under 1%. They proposed unknown large-scale topology bending the geometry of space itself, untestable with current instruments. 20 years on, no explanation has closed the case. If the largest patterns in the birthlight of the universe quietly point toward our own solar system's plane, then either we are cosmically unlucky, or the universe is not as indifferent to our position as the last 4 centuries of astronomy insisted. Why does the oldest light in existence seem to know which way we're facing? Alright, number 6. The Quadrupole Anomaly. George Smoot's team was not trying to find a missing signal. In 1992, working with COBE satellite data at Lawrence Berkeley National Laboratory, they were mapping the full temperature structure of the cosmic microwave background for the first time, cataloging every scale of ripple the young universe had left behind. The quadrupole, the largest, broadest ripple pattern possible, was supposed to be routine. Standard inflationary cosmology predicts a specific power spectrum, fluctuations of roughly equal statistical strength across all large angular scales, decreasing smoothly and predictably as you move to smaller structures. The quadrupole moment should sit comfortably within that predicted range. It came in roughly 7 times weaker than the standard model expected. Not once. COBE saw it in 1992. MAP confirmed it in 2003. Planck confirmed it again in 2013 and 2018. The single largest visible structure in the birthlight of the universe is quietly, persistently, almost absent. The MAP first-year results, published by Charles Bennett and collaborators in 2003 in the Astrophysical Journal Supplement series, reported the low quadrupole at a statistical significance that ruled out simple measurement error. 3 independent satellites, 3 independent decades, the same deficit. Physicists proposed foreground contamination from the Milky Way, subtracted using multiple frequency bands, deficit remained. They proposed cosmic variance. The idea that we simply got a rare draw since we can only observe one universe, mathematically permitted, statistically uncomfortable at roughly 1 in 20 odds. They proposed that space itself is not infinite, but finite, and small enough to suppress the largest wavelengths, a testable idea that current data neither confirms nor rules out. The deficit remains exactly where it was in 1992. If the universe is missing its own largest heartbeat, the question isn't whether we mismeasured it. 3 instruments built on 3 different principles all measured the same silence. What would it mean if the universe is smaller, in some fundamental sense, than the models assume? Alright, number 5. The bounce. Abhay Ashtekar was not trying to eliminate the Big Bang singularity by fiat. Working at Pennsylvania State University through the mid-2000s alongside Tomasz Pawlowski and Parampreet Singh, he was trying to apply loop quantum gravity's discrete geometry to cosmology, to see what happened to Einstein's equations when spacetime itself is treated as granular rather than smooth. Singularities were the problem he wanted to fix, not the beginning he wanted to erase. General relativity predicts that tracing the universe's expansion backward leads to a singularity, a point of infinite density and zero volume, where the equations themselves break down and time as a concept stops having meaning. This is the conventional Big Bang, not an explosion in space, but the beginning of space itself. Loop quantum cosmology's equations refuse to produce one. As density approached the Planck scale, a repulsive quantum geometric force emerged in the mathematics, halting collapse and reversing it. The universe didn't begin at a singularity. It bounced. Ashtekar, Pawlowski, and Singh's 2006 paper, Quantum Nature of the Big Bang, published in Physical Review Letters, showed the bounce occurring at a critical density of roughly 0, 41 times the Planck density, a specific, calculable number, not an approximation. The singularity was replaced by a bridge to a contracting universe on the other side. Physicists asked whether the bounce could leave observable imprints in the CMB. Proposed signatures remain below current instrument sensitivity. They asked whether the pre-bounce universe would have any causal connection to structure we see today. Models diverge on the answer. They asked whether the mathematics generalizes beyond simplified, symmetric toy models to the full complexity of our actual universe. This remains, after 2 decades, unresolved. The bounce works on paper. Nobody has proven the paper describes our universe. If loop quantum cosmology is correct, the Big Bang was not the start of time. It was a compression event in a universe that already existed, contracting toward a density it could not sustain before rebounding into everything you have ever known. Was there a version of the universe before this one that made the same mistake we might be making now? The next entry doesn't ask what came before the beginning, it asks what the beginning left behind. Alright, number 4, the cold spot. Pedro Villalba was not trying to find a hole in the sky. In 2004, working with a team at the University of Cantabria, applying wavelet analysis to Wilkinson microwave anisotropy probe data, he was testing the CMB for non-Gaussian statistical anomalies. A technical audit, checking that the universe's oldest light followed the expected random distribution. It found the distribution breaking down in one specific place. The cosmic microwave background should vary in temperature only by tiny, statistically random amounts across the sky, consistent with inflationary theory's prediction of Gaussian, scale-invariant fluctuations. No region should stand out as anomalously large or anomalously cold beyond what chance allows. In the constellation Eridanus, one region did. A patch of sky roughly 10 degrees across, registering nearly 70 microkelvin colder than its surroundings. A temperature deviation and an angular size that Gaussian statistics say should not coexist. Villalba's team published the detection in a 2004 paper in the Astrophysical Journal. A decade later, Istvan Sapudi and collaborators at the University of Hawaii, using Pan-STARRS 1 and WISE survey data, published a 2015 paper in Monthly Notices of the Royal Astronomical Society, reporting a supervoid aligned precisely with the cold spot, a region roughly 1. 8 billion light-years across, with far fewer galaxies than its surroundings. Physicists propose the void alone explained the cold temperature through the integrated Sachs-Wolfe effect, light losing energy crossing emptiness, but follow-up spectroscopic surveys in 2017 found the void too shallow to account for more than a fraction of the deficit. They proposed a cosmic texture, a topological defect from the early universe, mathematically exotic, never independently confirmed. They proposed simple statistical chance, plausible at roughly 1 in a few hundred odds, uncomfortably rare for the largest anomaly in the sky. No single explanation accounts for the full depth of the cold. Somewhere in Eridanus, spanning a volume larger than almost anything else ever mapped, the universe is colder and emptier than the same equations that describe everywhere else say it should be. Is the cold spot a void the models simply haven't fully explained, or a scar from something that happened before inflation smoothed everything else away? Alright, number 3. The Hawking points. Roger Penrose was not trying to find evidence of a previous universe. Through the 2010s, working at Oxford alongside Vahe Garzadian, Daniel Ahn, and Krzysztof Meissner, he was testing a specific, falsifiable prediction of his own conformal cyclic cosmology model, a theory where each cosmic aeon ends by evaporating into a smooth, low-entropy state that becomes the Big Bang of the next. If earlier aeons existed, their dying black holes should leave a signature. Standard cosmology has no mechanism for anything to survive the Big Bang. The CMB is treated as a clean slate, structured entirely by inflation's quantum fluctuations, with no information passed through from any before. Conformal cyclic cosmology predicts the opposite concentrated rings of anomalous temperature in the CMB, marking where supermassive black holes evaporated in the aeon before ours, their Hawking radiation compressed by the geometry of the transition into visible points on our sky. Penrose, Ahn, and Meissner published apparent evidence for Hawking points in the CMB sky in Monthly Notices of the Royal Astronomical Society in 2020, identifying candidate points in Planck satellite data consistent with the predicted signature, building on an earlier 2018 catalog of ring-type structures the same team published in the same journal. Physicists proposed the rings were statistical artifacts of the search method itself. A 2020 reanalysis using machine learning found that after removing a small number of unusually bright or dark pixels, the significant rings disappeared entirely. Physicists proposed the points were consistent with ordinary Gaussian CMB statistics once properly modeled, supported by multiple independent teams. Penrose's team disputed the corrections, arguing the analysis missed the specific elliptical distortions the theory predicts. As of this recording, the dispute between the discoverers and their critics remains unresolved and adversarial. Every photon in the CMB has been traveling for over 13 billion years. If Penrose is right, some of that light is older than the Big Bang itself, carrying the last radiation of black holes that died in a universe before this one. If a previous aeon really did leave fingerprints on our sky, what does it mean that most of the field looked directly at the evidence and still isn't certain what it's seeing? Alright, number 2. Inflation's own prehistory. Alan Guth was not trying to explain what came before the Big Bang. In December 1979, working at Cornell University on a problem in particle physics involving magnetic monopolies, he stumbled onto a mechanism, a period of exponential expansion in the universe's first fraction of a second that solved several unrelated cosmological puzzles at once. He wasn't looking for a new theory of the beginning. He found one anyway. Standard Big Bang cosmology, without inflation, cannot explain why regions of the universe too far apart to have ever exchanged light have almost identical temperatures, or why the universe's geometry is so close to perfectly flat. Guth's inflationary model fixes both problems by proposing the universe expanded by a factor of at least 10 to the 26 in a fraction of a second. Here is the problem inflation creates in solving the problem it was built for. A field capable of driving that expansion has to already exist, in some pre-existing state, before inflation can begin. The theory that explains the smoothness of our universe requires an unexplained something already present to smooth it. Guth published Inflationary Universe, a possible solution to the horizon and flatness problems in Physical Review D in 1981. Within a decade, Andre Lin's work on chaotic inflation, published through the 1980s, showed that once inflation starts anywhere, quantum fluctuations guarantee it never fully stops, spawning bubble universes eternally, each one a Big Bang for its own internal observers, with no defined beginning to the whole structure. Physicists propose the inflaton field emerged from a prior quantum vacuum state, which itself requires prior physical laws to exist, pushing the question back rather than answering it. They proposed eternal inflation has simply always existed, past eternal, with no true beginning, directly challenged by the Borde-Guth-Vilenkin theorem. Published in Physical Review Letters in 2003, which proved that any universe which has, on average, been expanding must have a past boundary, it cannot be past eternal. They proposed quantum cosmology replaces the question of before with a boundary condition, not a cause, a redefinition, not a resolution. The theory that best explains why the universe looks the way it does cannot itself explain what set it in motion, and a 2003 proof appears to forbid the most popular attempt to dodge the question by pushing it back forever. If inflation requires something to already exist before it starts, and infinite regress is mathematically forbidden, what is left to fill that first, unaccounted for moment? 9 specific violations. 9 specific failures to explain them. 1 entry left. Alright, number 1. The quantum fluctuation that started everything. Alexei Starobinsky was not trying to describe the birth of the universe from nothing. In 1979, working at the Landau Institute for Theoretical Physics in Moscow on quantum corrections to gravity, he was calculating what happens to space-time when quantum effects are included near a singularity, a technical extension of general relativity, not a creation myth. The math kept producing a universe that expands from an unstable quantum state without ever specifying where that state came from. General relativity, run backward without any quantum correction, terminates at a singularity. Infinite density, zero size, and no further questions the theory is equipped to ask. It is, by design, a wall. Quantum cosmology, developed further through the 1980s by James Hartle and Stephen Hawking, replaced that wall with something stranger. Their 1983 paper, Wave Function of the Universe, published in Physical Review D, proposed the no-boundary condition, a universe that doesn't begin at a specific point in time at all, because near the origin, time itself smoothly transitions into an extra dimension of space, the way the North Pole isn't a boundary of a globe, just a point on its smooth surface. Under this model, there was no moment of creation, because before is not a place the geometry of space-time allows you to point to. Asking what happened before the Big Bang becomes, in this framework, structurally identical to asking what's north of the North Pole. Physicists propose testing the no-boundary model against the specific pattern of primordial gravitational waves it predicts. Current instruments lack the sensitivity to detect them. Physicists including Neil Turok and Jobfeld Brugge published a series of papers beginning in 2017, arguing the Hartle-Hawking calculation, done correctly, produces mathematically ill-defined, divergent results rather than the smooth universe it claims, a direct challenge from within the same theoretical framework. Unresolved as of this recording. Hawking's own later work, published shortly before his death in 2018, attempted revisions that his critics say still don't fully close the gap. If Hartle and Hawking are right, you are not living in a universe that began. You are living in a universe that curves smoothly and without seam into a question that space-time itself is not built to let you ask. If there was never a moment before the beginning, what, precisely, are all 9 of the previous anomalies pointing toward? 10 anomalies. 10 teams of scientists who went looking for something ordinary and found the models breaking at the seams instead. None of these results come from the fringe. They come from Physical Review D, from monthly notices of the Royal Astronomical Society, from the same journals that gave us GPS satellites and gravitational wave detectors. The universe is not confused about how it began. We are. Every anomaly on this list doesn't sit at the far edges of what we don't know. It sits at the center of the theories we trust the most, the ones that have passed every other test we've thrown at them. That's what makes this list different from speculation. The cold spot is real. The quadrupole is real. The vacuum energy mismatch is real, measured, published, unresolved. Somewhere underneath the smoothest, most successful description of the cosmos we have ever built, there is a question mark the size of everything. If you want to see more videos like this, click the video on screen now.